Hello, hello, hello. Hello. Start a recording. Cool. Drew, I'm going to mute you if that's all right. I know how to do that. There we go. Welcome to the Design for Additive Manufacturing webinar. I am one of your hosts, Luke Gelman, and where is it? Okay, cool.
You online?
All right. Time to tell some additive manufacturing jokes written by ChatGPT. Oh. Hello, 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 everybody. People are starting to roll in, which means this is my cue to start telling horrible jokes. Hello, Colin. All right. I have some additive manufacturing dad jokes as written by ChatGPT. So I'm ready to roll with these. This is my comedy stand-up debut. How do additive manufacturing technicians stay calm under pressure? They keep a steady flow of cool filament. Heyo, right? But I need one of those. Exactly. Man, I got 3 minutes. I don't want to burn through my 16 jokes in 30 seconds. I would do that.
A lot of jokes.
It is a lot of jokes. All right, Kevin, this one's for you. You ready, buddy?
I'm ready.
What's an additive manufacturing machine's favorite type of music?
I don't know.
It's heavy metal. The answer's heavy metal.
That joke resonates.
Boom. I mean, you with over 20 years experience in additive manufacturing, I know your additive manufacturing jokes are way better than ChatGPT's. But we're not
They
gonna
usually are, but usually I just use my boss's names over the years. That's the biggest jokes.
Perfect. All right. Oh man, I got another one. What is an additive manufacturing machine's favorite holiday? Prince-giving. Hey-o, Prince-giving. Got that?
I got it.
Yeah. It's good stuff.
I don't get it.
It's fine. We're just keep on moving. Doesn't matter if you get it or not. What did one 3D printer say to the other at the party? Let's make a PLAce to go, or place to remember. PLAce to remember. Get it?
I get it.
PLA, because it's PLA, it's a filament. You get it? Got it? Okay, cool. All right. Why did the 3D printer go on a diet? It had too many extrusions. Oh man.
Medical issue.
Right? Exactly. Why did the 3D printer get an award? It had outstanding print performance. These are all written by Chat GPT.
Artificial jokes.
Yep, these are virtual jokes. Okay, we're just telling some more jokes while people make it in here. We're still another minute to go. So, why did the 3D printer break up with the photocopier? It felt like it was just making copies of itself.
Uh,
Oh boy.
Yeah, it's bad. I know.
That's bad. That was bad. I don't even get it.
How does look? You're asking virtual, artificial intelligence to write jokes about additive manufacturing. You get what you get. How does a 3D printer express love? It says you're the ABS salute best. Make sure we're letting people in. What's going on, guys? I'm just telling some ChatGPT dad jokes about additive manufacturing until we get started. We're just gonna, go. I'm gonna go for another minute or so. I'm gonna try to end it on a high note. Okay, what did the 3D printer say to the filament? I melt for you.
Oh,
Can I try one?
Yeah, go for it.
So how do you know when a 3D printer a metal 3D printer is resting?
How?
It takes the powder.
Oh, nice. All right, we're gonna go for. I'm gonna go for a couple more, and then we're gonna get going. What's a 3D printer's favorite dance? The robot. Heyo. Right? Okay, Kevin, this is for you, man. How does a metal additive manufacturing engineer answer the phone? Alloy there.
That's
Okay, and I'm gonna do one more just because
They're getting better.
they're getting better. I'm gonna do one more, and then when we're gonna get into this. Okay. How does a 3D printing engineer apologize? Sorry if my last joke was a bit layered.
That's really good.
Yeah, it was good.
That's a high note.
Yeah, absolutely. Okay. So I don't want to, keep everybody, you guys didn't come here for my humor. You guys came here for to learn about additive manufacturing. So welcome everybody. Let me just get one more thing set up, and then I can do less talking and more clicking. Okay. I am Luke Gelman. I'm Director of Sales at Fastway Engineering. I'm very excited today to have some talented team with me to talk about additive manufacturing. I myself have a lot of experience in sales, and I am really good at helping people get access to ANSYS tools. Along with me today is my partner, Jim Shaw.
Wow, thanks, Luke. And just so everyone knows, we are recording this, so we'll have this available to everyone afterwards. But my name is Jim Shaw. I've got a couple decades in simulation, aerospace, automotive, et cetera, et cetera. I'm a structures guy, but I've fallen into more heat transfer and fluid simulation, which all three have applications in additive, and I'm super excited to share some of that with you today.
hi everybody. I'm Karen Novotny, founder of 3D Metal Consulting. I primarily identify as an artist, but I'm a mechanical engineer, a forever curious student. And for the past decade, I've worked in factories in the South, the Midwest, and the West Coast of the United States in operations management positions before starting up 3D Metal Consulting. And now I work very closely with my business partner, Kevin.
So, hi, Kevin Ayers here. I've been involved in additive since 1993, first the FBI, then SME, then Danfoss, now 3D Metal Consulting. I've done thousands of designs and 10,000 plus parts in additive for automotive, aerospace, consumer products, electronic packaging, medical, etc.
Awesome. So today we're going to talk all about additive manufacturing. We have the physical side, the real world with 3D Metal Consulting, and then we have the virtual side with simulation with Fastway Engineering. And we're bringing them together to give you guys real solutions that are going to impact your company. Today, we're going to understand the capabilities of additive manufacturing, the speed of the prototyping process, lowering testing costs, and creating better products. In the end, we're going to hopefully bust some myths about additive manufacturing.
So if you see this quiz time emblem, the red and black emblem throughout the presentation, that means that you answer in the sidebar chat. So go ahead and click chat and open up your sidebar. You can tell us where you're calling in from and type your quiz answers there. There's going to be quiz questions sprinkled throughout the presentation. You have 10 seconds to answer, 1 answer per person. And if you get the most questions right, you win a $100 Taco Bell gift card. So let's dive into it. Quiz question number 1. What is the global valuation for the metal AM market in 2023? 10-second timer, go ahead. Type those answers in the sidebar chat, A, B, C, or D. All right, time's up. And the answer is more than $2 billion. So some say as high as even $50 billion. And most corporations using additive are not reporting it out either, like AM centers, garages, workshops, small service bureaus. So the main takeaway here is that traditional manufacturing market, which is roughly a $27 trillion industry, more than 2 billion of that is the metal AM market. So a lot of money is going here. All right, this can be a crowded graph, but go on Google, print this metal additive manufacturing technology landscape out because it contains a ton of awesome information. So I'm going to briefly explain what's going on here. On that center ring there, that shows what feedstocks you can use for metal additive manufacturing technology to turn it into metal parts. So here, powder is an example of a feedstock that you start out with. On the outer ring where it's green, those are different type of technologies. So there's a lot of different type of metal AM technologies. And then once you kind of decide which direction you want to go, then you can go to that outer ring, which shows a lot of the OEMs that make the metal printers for those technologies. So as you see on the outer ring, there's a lot of OEMs out there. There's over 200 metal AM OEMs. It can be a difficult industry to navigate, and that's why we're here for you.
So this is typical of a lot of the current documentation forecasts of what size the market is. I think these forecasts are very conservative. It wouldn't surprise me to know that these numbers are 10 times what they're saying, because it doesn't take into effect the value of the part when it's finished and the valuation the company will put on that part. So it could easily be 10 times higher than this. So I like to think of additive in 3 buckets. You have rapid prototyping, models, training aids, sales pieces. You have tooling, jigs, figures, lift mechanisms, 5S parts, storyboards, and molds that you might make. And then you have serial manufacturing, or people call end component manufacturing.
Yeah, so when we look at that industry sort of from a top-down perspective and look at the technology that we're using as designers and engineers, we kind of look at it in the simulation world in 6 different categories, starting off with what I think is the most important, which is called DFAM, right at the top in the center, or design for additive manufacturing. So we've got a handful of slides and examples today of the new suite of tools, both on the geometry CAD side and of course on the simulation side, and then of course how the two get merged together. The other 2 categories that we're going to focus on today, because we don't have enough time to do all 6, one is process simulation. So we're actually going to show examples of simulating the actual printing process and the level of detail of the physics that we can do there. And then, of course, on the part qualification side. And this is where we see not only a lot of, say, measurement and verification and validation on the physical side, which Kevin's going to cover, but also a lot that we're doing that's digital, right? That's on the actual, say, traditional FEA or CFD side. So if we dig in a little bit deeper, again, what's really new in the design world from a geometry and CAD standpoint are a couple of technologies under DFAM we call generative or topology optimization. We have an example just to the right of that, and lattice structures. So these are two categories, if you will, of incredibly complex geometry that humans or traditional design approaches just can't be used. We're dealing with complex surfaces. We're dealing in some cases with thousands and thousands and thousands of, say, beams and nodes for a lattice structure. And so there's a whole new suite of design tools, CAD tools, simulation tools, and the blurred lines in between that allow us as designers to create that geometry. And the geometry is so efficient and so complex, it can only be manufactured in an additive way. We're also going to be talking a bit more about that process simulation, like I mentioned. We're going to be able to show you an example of a true transient thermal structural analysis that is emulating the printing process layer by layer, or in some cases, basically cell by cell. So we can break it down to all the quality metrics that we're looking for. And then, of course, anything from a material decision standpoint.
Quiz question number 2. Thanks, Jim. How can you increase the odds of having a perfect print on the first try? 10 seconds. Time's up. See a lot of E's in the sidebar there. The answer is E. So you're going to want to run that simulation, having the experience on your side, getting navigation from experts like Jim. He's spent decades doing this stuff. And then making sure the machine is plugged in. Answer is E.
So we're going to do a quick overview of the metal AM technology market. The first thing we're going to look at materials. So a good way to start is looking at a part you may have in your company, what alloy you use it, how critical it is that you need to use that particular alloy. It may not be available in additive, so you may not be able to do that part. But a lot of times, increasingly, especially with binder jet, using a MIM and powdered metal, it is available.
Yeah, so let me give you an example of that using one of the tools that we have called the ANSYS Granta Selector. Now, this is a database. It's connected and has access to the whole CENVOL additive manufacturing database. But let's give an example of, say, you're a designer and you're working in the, say, the space race that we're seeing right now, which is really, really awesome. And you're designing a satellite, right? We've got an example shown on the screen here. And a very, very, very common alloy that we use in traditional CNC manufacturing for launching things into space is 6061 T6 aluminum, probably the most common by far. And so if I were a designer and I was tasked to say, hey, I want to redesign this part or this assembly and make it, fit for an additive manufacturing process, the first thing I'm going to want to do is try to find a material that's as close as possible in its physical and mechanical properties, right? I cannot 3D print, if you will, or use 6061 T6 exactly. And it's certainly not going to have the same material properties that it would be in a forged state, for example. So I want to look at things like stiffness and strength, right? Modulus elasticity, density. And I want to make sure that I find an alloy that's fit for an additive manufacturing process as close as possible to 6061 aluminum. So I'm going to be targeting specific processes like binder jetting, DED, or powder bed fusion, right? Where, through a little bit of cursory homework, I can see that I've got some alloys that are very, very, very similar. But in my research project, if you will, and every single design process starts with research. What I also want to do, a constraint that I have, is minimize or remove the chances for any sort of post-process stress relief. And really, I want to remove as many or minimize as many post-processes as possible. I want to get the part as it's printed right out of the machine and put in a box or sent to a customer. And I am a graphical guy. I'm a CAD guy. I'm an SPA guy. So I live and I want to see these in a graphical result. So let's show you an example of what that looks like. So the graph on this upcoming screen here is going to be a combination of a whole family of tools and of materials. And what I've highlighted here is the conventional 6061 T6 you can see in the bottom and the center. And then just to the right of that, with a slightly higher tensile strength, is going to be the EOS aluminum ALSI 10MG. And what I've done is highlighted what the software came back and told me is the closest possible alloy that fits all of our requirements. And as you can see in the upper right-hand corner there, it might be a little small text, but this is a powder bed fusion process. And underneath that, you can see that this does not require post-processing. So, you know, by my research and materials, I've nailed it. I also have, if I look at the graph, maybe a dozen or two more that are highlighted here. And I can judge whether or not they are similar both in density and in tensile strength. So that would be a very, say, quantitative and formal sort of engineering approach for selecting the material before you move to the next step.
Okay, quiz question number 3, talking about materials. Which metal with high thermal conductivity and reflectivity made recent breakthroughs in the AM industry as technology improved? 10 seconds. Time's up. Nobody answered vibranium. And the answer is C. So traditionally, copper powder has been really difficult to print with because of the energy. The energy dissipation was so high with the laser. But now that's different. I mean, look at that part. Check out that resolution. You know, we're printing crazy stuff nowadays. That's copper. Yeah, next slide.
So we're into the next big topic, which is really coming to vogue. A lot of people are providing training for this, designing for additive manufacturing. So some of the key points is you have a completely different design philosophy from normal manufacturing design. It requires new tools. It requires a different mindset and a creative mindset, which is a good thing. You've got to be concerned about dimensional control of the part and key surfaces and have repeatability and standardization that you would have in your manufacturing standards protocols. Okay. So traditionally, you know, some of us give us a hard time in the additive world because we have our own design methodologies. But really, if you look at CNC machining, injection molding, casting, forging, stamping, even MIM, they all have their own design rules that you have to learn as a designer if you're going to make parts successfully for those processes. Additive is different. You got to worry about the orientation of the part and how you're going to build it to make sure your feature sizes are within tolerance and will print out. You got to worry about if your process going to require supports, where are they going to be at? Are going to be able to remove them, especially if you have internal features like flow channels. And then you got to worry about materials again and designing for that particular material made in additive. And then post-processing, how you're going to bring your part into spec, especially for seal surfaces, bearing surfaces, things like that. So here's an example of, it's not a very sexy part, but it's an antenna. But you did 95% lightweighting on this antenna. And it reduced costs several different ways and did a lot of value added enhancements to the process and less operational time to do it. And the lead time to going from one design to another was reduced dramatically. I can't emphasize how much product development time is reduced using additive. Okay. So in additive, we talk about living hinges and mechanisms like that you can print all in one piece. I had a design where we had a flow into the part. We were able to use geometry internally so that as the flow pressure increased, it changes the cross section of the flow and gave you enhanced performance and good energy that way. So again, we're having to redesign things and think things differently in additive, and you get so much benefits from that. You increase part functionality. Complexity is not only free, it's easier to make geometry in additive if it's more complex. You can do functionality within the same part. Lightweighting is big, especially with increased sustainability issues and demand for more energy efficient designs. Next. So I've did a lot of designs and product development of pieces over the years, and these are the basic building blocks represented in circles. But every one of these, as you go from one to the other, you can go back in a loop and go backwards and redo it as you analyze the design, as you get more people involved from manufacturing or management or marketing or in sales. And because of this forward, back, and looping, product development times can take 2 or 3 years sometimes to successfully lay out a part. Jim?
Yeah, so if we compare that to what the current process is for additive, we take all those factors, right? So price or cost, function or performance, reliability, et cetera, right? Design for manufacturing, DFM, DFA, right? So we factor all in at the same exact time, right? And that's challenging for humans to do. I mean, we're pretty special animals, but at the end of the day, like to take 4 or 5 or 50 different parameters and put that into software and try to optimize it within that is pretty challenging. And that's why the new sort of suite of tools, right? So generative topology optimization, lattice, et cetera, those are all sort of algorithm based, right? And what those algorithms do at the end of the day is kick out or export a geometry. What goes into that is all of these different parameters. Again, cost function, DFM, DFA, and it can apply a whole host of different sort of technologies or code and can give you 10 or 100 different options. And then at the end of the day, you can pick the one that might look a little bit better or, print a little bit faster, let's say. So, it's really not replacing the designer, but making the designer more effective. And as Kevin mentioned, I mean, to really optimize a part or an assembly for a production process can take years, right? We'll do an initial launch, and then for the next 6 to 12 months, we're trying to make it better, and cheaper. But now we can do that all at the same time, and we can launch the product faster to market, and when it gets there, it's going to be more optimized. So let me give you an example, and we're going to take the previous example of an aerospace application, right? So we've got this low Earth orbit small satellite. We call it a CubeSat or a nanosat. And in this sort of vertical structure at the top is actually a camera. So let's call this sort of a weather satellite taking pictures of clouds or something like that, okay? So we've got this camera, this optical assembly, and there's a big chunk of aluminum, right? 6061 T6. That is massive, too heavy, plenty stiff enough. But every ounce counts in aerospace and a lot of industries, right? So we have a design requirement to remove 91% of the mass. So how do we do that? Well, we could say do a traditional CNC approach, which would require at least a few years in the experience and working alongside a CNC machine shop or the floor and understanding what the limitations are and what the constraints are of that machine. So in the second column, you can see I've got this example of a CNC machine part. Don't judge. I did that one myself. Don't judge. It's pretty simple, right? A lot of sort of XYZ planes and a couple of rounds on the edges. So as a designer, I was able to successfully reduce that mass to 0.1 kilograms. And the performance metric that I'm using in this case is what's called the first mode frequency or the resonant frequency. And in shock and vibration, which this part has to be able to withstand through the launch process and through the orbit, we have to make sure that that number is as high as possible. So the baseline frequency was almost 4 kilohertz. So my human approach of traditional CNC got us around 2 kilohertz. Why don't we compare that to an additive approach, right? So we've got topology optimization and we've got a lattice approach. And as you can see, complex geometry, I can't manufacture it any other way. But by using topology optimization, not only did I hit my 0.1, which I also did with lattice, but the frequency is almost as high. This part is almost as stiff as that gigantic chunk of 6061 T6 in the left-hand side column. That geometry that's highlighted in red right now is not something that really any designer, and now maybe some, I know a couple that are really good. Kevin's really good, but a lot of designers really would not be able to come up with that geometry without some significant help.
Okay, quiz question number 4. So like Jim was talking about, if you're manufacturing a structure for an optical assembly or a jig or some sort of fixture, when is a good time to deploy simulation when making that part? 10 seconds. All right. No, it's not E. The correct answer is B, initial design. So, you don't want to wait till too late in the game to start applying simulation. You want to get that very early on during the initial design.
So we've talked about the first 2 elements in here. Now we're on to the nuts and bolts of things, verification and qualification in additive manufacturing, which is now really coming into vogue. So we have to verify the materials. So we'll get a batch of aluminum powder, for example, and we're going to want to run some testing on that, especially using test coupons and dog bones to build them in different orientations and test them. You need to verify the process. You've got all kinds of scanning mechanisms you can help you do that, and then do the GD&T of the individual components to make sure they're holding 2-dimensional tolerances for manufacturing, and then the component qualification for a part, which normally you have to do anyway in the other manufacturing process. And the PPAPs can be a little more involved in additive. I'll give you a little heads up.
All right, thanks, Kevin. Quiz question number 5. What is a common part approval process used for 3D metal parts in the automotive industry? 10 seconds. All right, time is up. The correct answer here is PPAPs, production part approval processes. So you can work with experts like Kevin. He knows a lot of the best practices out there, new developments. It also helps to really understand multi-physics, and understanding FEA is critical.
Yeah, that's a great great point, Kara. I'm going to dig in a little bit on the FEA side as well. So, before we get to the production part, a lot of design validation occurs. And this is the type of simulation that we've been doing for quite a long time, right? Your traditional structural analysis, thermal analysis, fluids, et cetera. But what's new is, because of our DFAM process, creating really complex geometries like lattices and very organic looking smooth surfaces from generative and topology optimization, that does actually push some of the existing tools that have been around to their limits. And so we're starting to see new ways of analyzing it. For example, that lattice feature, or that lattice part in the upper right-hand corner, has a lot of surfaces, like potentially thousands and thousands of surfaces. So we've got new methods to say discretize that before we solve it. And so, we're seeing new investment in the tools to handle some of these new geometries. On the fluid side is really interesting, right? So here's an example in the bottom left and towards the middle, where we've got these triply periodic minimally surfaces, which include gyroids, right? And if anyone's been to Formex, which was just happening a few days back, or any other show, you will see dozens and dozens of heat exchangers, right? It's one of the, I'll say what Kevin says, it's in vogue right now. It is a very, very popular approach for additive, because we're pushing heat exchangers to the highest possible performance limit, pressure drops and heat exchange rates, and they're not nearly as expensive as a traditional, say, finned aluminum radiator, right? What I think is the most coolest part of it, though, is what's happening on the electronic side. So we are doing additive for electronics. We haven't done for a little while, and one of the key features there, again, we're using copper, right? Or a very, very similar alloy that is very thermally and electrically conductive. And we're doing it on very complex surfaces, or we're doing it on very flexible surfaces. So here's an example of a flex circuit that's been manufactured. And what can come into play with some of these curved surfaces is that we have electromagnetic interference. And so these tools that have been around for decades doing traditional EMI, EMC, say on straight flat rectangles, are now having to be updated to handle some of the more complex geometries that we're doing in additive, which is really cool stuff. But what I really want to show you is what I think probably the latest and greatest and the neatest thing, which is a true, what I would call full physics simulation of the actual process. So this has been out for a few years now and readily available, right? So I mean, outside of academic, we're not writing code anymore. This is readily available in commercial code. And this is an actual transient model. So it is layer by layer. It's actually down to the cell by cell. So we can actually discretely, say we're not showing the print head here, but we are showing intermediary through each layer. It's a full thermal structural model. What we're able to do there is actually predict not only what the geometry is or where the best place to put some of the supports are, but we're taking into account that we have this thermal profile, right? We're heating this thing up. We have a phase change on the material. At the end of the day, it's going to cool down. And what happens when metal cools? It deforms. And so this process, which takes the true slicer file, which would traditionally go into a 3D print machine, actually goes into our FEA. So let me show you an example of that. What we're doing is not only predicting the printing process, we're predicting the distortion, and then we go one step further, and we actually compensate for it. So here's a great example here of a cylindrical filter from Croft. What happened was a traditional process. You've got your lattice tool, your DFAM tools, you go through your whole thing, and then you say, you know what, let's just print it, let's go. And what happened was, as the cylindrical filter was printed, due to the thermal profile and the heat that built up into this lattice structure, you can see at the top on the left-hand side where it says print, the actual geometry kind of necked down a little bit, which was out of spec. And again, if we're going to go through this effort of using additive manufacturing, the goal is to get a part that is as close as possible to what we call net geometry, or the actual part. No post-processing, no finishing or anything, just pull it out of the machine and put it in a box. And so what we do is, by predicting how much this part distorts by doing a full transient thermal structural analysis, we take that knowledge, we go back into the CAD file, and we pre-distort it. So we're actually necking it down because we know that as it cools from the printing process, it's going to expand into spec. And what you see on the far right-hand side is a lot of design and analysis work that at the end of the day, when somebody hits the print button and the print's set up right, the machine's set up right, you're going to get your net geometry, put it in a box, and ship it to your supplier.
So we're on to the final item on the metal AMO view, cost. So in every company in manufacturing, you'll have a spreadsheet with items in there. And additive has some different items in there with bigger weights. The additive cost of the machines are, especially metal, can run from 120,000 to $2.5 million in the hybrids. So you've got to keep back the fact that the system life is how expensive it is. You've got to do facilities cost to put those machines in there, and maintenance regularly to remove powdered material. In operations, you've got to keep track of the labor, and the skill sets in additive can be high. You got to post-processing costs if needed for like bearing service, seal services, things like that. And then the qualification, testing, and failure analysis of the parts. And then another item, software and simulation. There's all kinds of cool software out there, including textures, but especially simulation. If you're doing metal, you need to have a simulation to get that part done in a reasonable amount of time. So some key points, some pain points too mixed in there but there is a lot of benefits for simulations. You can really reduce the time, the cost per part, and part of that is the time, which is a big factor. You want to reduce the defects. You want remove unforeseen costs, and you can do that through simulation. And you want to do things in-house if you can. That will save things. So designing it, manufacturing it, and having the software to do that is a big part of the equation. And I think we're seeing now, because of COVID, we're seeing supply chain disruption being the new norm. And so additive in metal is going to help you get by supply chain issues. Next. Here's a case study of a part Sayaki did. Realize you got some internal geometries inside this part, but they were able to reduce the cost of the part, the time to manufacture the part, and reduce waste. It's big these days, becoming a bigger issue to be able to check that sustainability box to show that you have less waste in the system. Next. This is a part that I came from that I was involved with a little bit, but instead of doing a three-dimensional array, we're able to do two-dimensional array and build these parts as needed, do true on-demand manufacturing using additive for the first time since on-demand manufacturing was really created. And you can really get the cost down to reasonable cost that makes it all worthwhile.
Yeah, so here's an example, and and Kevin mentioned that there's a cost to the new tool set, right? The DFAM tools, the simulation tools, topology optimization, lattice, et cetera, right? And so how do we justify those costs, right? So here's an example of a rocket injector. The end of the day, it went from 50 something parts in the assembly to a single part. That's a big deal, right? And it was done by simulating the full thermal stress profile of the printed object. And you can see in the bottom right, that's not an insignificant, model to build and do. But at the end of the day, it's justified. How? Well, we just went from potentially 50 different suppliers of 50 different parts, or maybe 10 suppliers, right, to one supplier. Okay, so there is an overhead every time you have an extra supplier. And there's a lot of OEMs who are looking for reducing the number of suppliers, right? Kevin just mentioned supply chain issues. We had them before COVID. We really had them during COVID, and we're still managing them a little bit here post-COVID. So transportation, inventory holding, and labor costs, those sometimes don't show up, if you will, in the bill of materials, right? They don't show up in the CAD model, but those are real costs that are incurred when you have to move parts from A to B, especially if they're big or if they're heavy. You have to hold them. That's not free, right? It's a real estate cost, whether you're doing it or you're using a 3PL. And then labor cost, right? At the end of the day, we're not trying to replace everyone with robots here, but what we're trying to do is use skilled labor where it's necessary. And in many times that is in the quality side. So when we're doing quality inspection, say a part comes in, hits the dock, goes to quarantine, and you do your inspection, at least now we can inspect a single complex part instead of 50 maybe less complex parts. And since up until the printing process, everything is digital, that means we have a digital file, we can use a 3D CMM machine, and really the only thing that happened to be in the physical world is the actual metal itself that we're sending off to a customer or something like that. So it does require investment, right? None of this stuff is free, and we now know that this is a huge market of opportunity and investment. And so really what a lot of companies are looking at is when's the payback. And by looking at a methodical process like this and tracking costs of not just parts, but also intangibles, say like transport, inventory, labor, it's pretty clear that the payback is quite quickly, and that's why we're seeing this technology being rolled out in pretty much every industry.
All right, thanks, Jim. And that brings us to our final question. We might have a few people tied right now, so we're going to do a tiebreaker. No longer multiple choice. You're going to write an actual number in the comment this time. So how much venture and investment funding went to North American AM companies in 2021, according to our friends, Global Barnes Advisors? Luke in the garage with the 10-second timer. Thank you. All right, and the answer is 5.3 billion.
Are we doing Prices Right rules?
Absolutely. We're running a tight ship here. But guys, this has been really exciting today. We've learned a lot, and hopefully we've busted a few myths about additive manufacturing. Some of the myths that we covered today are, that all additive manufacturing machines are equal. Choosing the correct machine and material really doesn't matter. That is not true. Additive manufacturing is always the best manufacturing option. It is not, but it is a way that you can reduce cost and solve some real world problems. In-house manufacturing experience is not recommended. That it's it does help, and we're here to help with it. Designing for design for additive manufacturing parts is the same as for non-additive manufacturing parts. That is untrue. You could do things with additive manufacturing that you could never do with traditional part manufacturing, like internal structures and things like that. And the last one, you won't need in-house peripheral supporting technologies and staff, post-processing, machinists, metallurgists. That is also not true. If you have the right people in-house and you have the right tools and the right support, you guys are going to have a lot of success and you can do things that you've never done before.
All right. So if you like what you heard in this webinar and you are interested in working with us, Kevin is one of the experts on the 3D Metal Consulting team. We have a growing team of over 10 plus experts, over 200 years of experience on frontline manufacturing operations. If you attended today, congratulations. You get a free consultation with us, but we only have 9 spots available for 1 week in December. So watch out for your email. I'm going to send a link out. It is a $100 value for a consultation, but you're going to get a special link to sign up for a free webinar. Sign up quickly because those spots will get filled. And if you want to follow us more, we're on LinkedIn, we're on YouTube, and we're going to be posting a lot more videos about 3D metal printing, the printers itself, the industry, things like that. We're going to be doing a lot of videos in 2024. So stay tuned. We've been starting up for over 2 years now, and we're here for you. We're ready to go.
Yes, for some of you inquired, we had a webinar scheduled earlier, and I had a personal tragedy. My daughter, Suzanne, died. She was really an interesting person, full of joy and loved life, and it really hit us hard. But thank you, and sorry there was a delay in the webinar.
Okay, guys, I would like to thank my co-presenters, Jim Shaw, Karen Devotny, and Kevin Ayers. We are open to any kind of questions you guys have. We really appreciate this webinar. We'll just put your questions in the comments. But we are going to post this video online for you guys to view it later. We will have the presentation online for you guys to download. But if there's any questions you have, we'd be excited to answer them. Well, if you guys want me to tell more dad jokes about additive manufacturing, that's always an option as well. But seriously, guys, we really appreciate you guys' time today, and we look forward to. We do have a question. Is additive manufacturing limited to small quantity and weight-sensitive industries like automotive and aerospace?
So I'll answer that. We want to answer it. So it's not anymore. We've got a lot of new machines out there now that have big build platforms and do it much quicker. Some of the older metal technologies in powder bed fusion were kind of slow, but binder jet and wire, 3D printed sand molds and things like that are becoming much, much quicker. So we can do production runs 3,000, 5,000 now.
And just to add on to that, sorry, just to add on to that first one, because that's a really good question. Some of the sectors that it caught on really fast with is aerospace, automotive, medical, dental, and tooling industries. But now we're starting to see even more applications. Kevin and I have a really strong background in more legacy manufacturing. So thanks.
Yeah, parts and services is becoming bigger now. So doing production runs of 50 to 100 are making a difference.
Yeah, and I would say from our perspective on sort of the tools and the software and the DFAM side, and again, a slight bias here. I'm not quite sure who asked the question because we have seen so much in the aerospace. But at the end of the day, those are, say, higher risk, higher criticality, and higher margin type parts, right? So that's where we see a lot of leaders in the industry take on new technologies, right? It's just not the first time, say, the quote unquote defense industry would have been applying, some of the tool sets because there's so much at stake, right? When we're talking about aircraft and medical, we're talking about literally lives are at stake depending on the application. So that's where we've got a huge upside, and those industries can handle, say, a new technology which hasn't been, say, economically available, right? But automotive has massive volume, requirements that aerospace and, say, medical don't. So in the automotive industry, while they're still doing all their PPAPs, and we're starting to see additive come out like in brake calipers and other applications, maybe on the inside, that's going to reduce the cost because it's going to get picked up by so many different suppliers, right? OEMs, tier 1, tier 2, tier 3. And every single day for those, especially Kara and Kevin, who are like literally paying attention to the technology, is changing every single day. The software changes maybe once or twice a year, but the actual technology of new machines and new processes, it's like every week you look online and it's something totally different. So we're going to start to see it really rolling into everyone else, more consumer-based stuff as it gets a little bit more economical. That's my 2 cents anyways.
Got another couple questions. What's the easiest to deploy / use metal in LPBF?
Oh, that's a good question. From my experience in powder bed fusion, 17.4 stainless was the easiest metal to build. There were some applications for 6820, which is very difficult. Cobalt chrome is hard to heat treat and stress relieve at times. Titanium is used well, but you're worried about material costs sometimes in there, make a good part. I think 17.4 is the easiest. 17.4 is how to use.
Okay. What about using ANSYS for WAM?
Yeah, I can certainly pick that one up. So WAM is an example of the directed energy deposition or DED process, and so the way that the transient thermal structural analysis capabilities are coming out is this companies like ANSYS are targeting a certain process. They'll partner up, just like we're partnering with 3DMK, they'll partner up with industry experts and academia to make sure that the parameters of that process, right, energy required, phase change, et cetera, to get the thermal profile and what the resulting material properties are, that takes a little while to do. So they're out there with 3 different processes. DED is one of them. I don't know off the top of my head specifically if it includes wire arc, but Sarah, certainly I'll get some more homework for you and I can email you afterwards. But that's a great question.
Thank you, guys. Got another question. For internal fluid pathways without supports, teardrop shaped channels are recommended. Is there a software product available that can add this geometry? This with respect to build direction seems like it's a well-known recommendation without a solution.
Yeah, I can hop on that one real quick. So, teardrop shaped. I'm not 100% sure what kind of profile you're talking about, but let's say you wanted to design a heat exchanger, right? One of the challenges that we mentioned a few slides ago is we have an awesome suite of software that can automatically create gyroid structures and other TPMS structures, changing the density as a function of distance, right, from the inlet to the outlet, multiple inlets, multiple outlets, et cetera, et cetera. So at the end of the day, what's happening right now is those companies are able to predict an optimized heat exchanger, print one, not print 30, or manufacture a variety of different densities and narrow cross sections and geometries. Print one and test it out. 2 of the key things that we're looking for, right? Pressure drop, so we can have our fluid pump, whether it's a gas or liquid, right? And ultimately, and we had a picture on a couple slides ago, but if you want to know what the perfect profile is, teardrop or otherwise, right, it's going to come down to the performance of the fluid, right? And making sure that we have, thermal boundary layers and fluid boundary layers. So, I mean, if I had all the tools at my disposal, I'd be using a CFD tool. I'd be using something like Fluent, right? That would be predicting what's that shape. I think that if there is no access to those tools, it's good to use design guidelines and things that we find online, like quote unquote teardrop shape, but really it's very, very specific to the local velocity, the flow rate, and the operating fluid, its viscosity, density, temperature, et cetera. So, I'm going to go with a pretty, I'll say consulting type response here where it's like, it depends, but certainly you have to account for the fact that as you move fluid internally from an inlet to an outlet, that pressure is dropping. And you want to make sure you can control that. Otherwise, your pump's going to be too big or your flow rate's going to be too small and you're going to heat soak. So I don't know if that that answered the question there, Nick. That's a fantastic question. And I think that we're living in a time right now where a lot of companies are trying to share, what geometries work and what don't. So for those who maybe don't have access to the tools, can start to narrow down, what they can prototype and what they can print. So I don't know, Nick, if that kind of answers the questions or not, but
let me chime in there real quick.
So yeah,
so
absolutely.
The value of the teardrop is that in a certain build orientation, you're not going to need to build supports on that shape to build it. And what normally had to be done, you could get so far with simulation software in the past, but then you'd go in and the channel would move X, Y, and Z, and then you'd be left with support structure still in there. And I guess they're trying to figure out is enough AI in the software now where you say is don't put support structure in this piece because I can't clean it out. I guess that's what he's trying to say. Yeah.
Yeah, I got you there. Yeah, so most of the generative software, most of the additive focus, so TPMS, gyroid stuff, I mentioned you're driven in some cases by the fluid performance, but absolutely build direction is one of them. So like Kevin said, you've got a certain, say, overhang angle. You don't want to go over 45 or even near 45 for tolerance reasons. I don't know any additive DFAM software that doesn't include that as a parameter. So, I mean, that's one of the first ones that was added.
Okay, great. We got one last question, and then we're going to wrap it up for the day. Again, I wanted to, on behalf of 3D Metal Consulting and Fastway Engineering, I just want to thank everybody for hanging out with us and learning about additive manufacturing. So the last question we have is, do you need to be an industry expert to use ANSYS software?
Yeah, I mean, that's definitely a loaded question. Sorry, you want to mute real quick? Yeah, no worries. Yeah, Luke and I are 3 inches away from each other. I think that's definitely a loaded question. Most software nowadays have a variety of different capabilities, each with their own learning curve and their accuracy or their precision, right? So, there's software out there. I mean, if DFAM software required quote unquote 10 years of experience or years of experience, that would slow down the deployment of additive. That would slow down the number of people who are interested and able to pick up these tools, right? The purpose of these tools is to automate. And again, Kevin had like 4 or 5 or 6 parameters that all had to go in series, and you're looping back and forth and taking 2 years to develop something. And the whole purpose is like we automate some of that sort of parallel consideration, cost, DFAM, DFA. The tool's got to be doing that automatically, right? So there's this careful, I think the challenge in the software industry, there's this careful balance between I need to make it easy to use. I don't want somebody to require a PhD to do generative topology. It requires a PhD to code it. Let me just get that straight. But again, nowadays we're not writing our own code to do it. We're using commercially available software. So I think that as the software companies start to build out their portfolio, you're going to see multiple offerings. And in the case of ANSYS, which was the specific question, there's a couple of different offerings, right? There's offerings that make some simplification, some automated meshing, for example, and you can fluid flow through a heat exchanger. But if you want to match that to within 1% of test data, yeah, that's going to require a more traditional, meshed CFD tool. So great question. Thank you.
Okay, guys, thank you so much again for joining us today. Look for us on LinkedIn, and we'll be sending out follow-up emails with links to where you can find the presentation to share with your colleagues and everything else. So thank you so much, guys.
Thank you all.
Take care. Thanks, everybody.